day to you. This is Anagalactic. So where we left off yesterday was with me making the preposterous claim that the quantum is an illusion. Well, it would have to be because no one can even define what it is. And yet everybody talks about it, don't they? The quantum this, the quantum that. At the very end of the lecture yesterday, I promised to tell you what the quantum actually is. There does have to be a quantum. But let's make sure that we know what we're talking about when we say quantum. There are two terms that have been known of for about 250 years, and it's resurfacing, believe it or not, but it'll never make headlines, unless I make headlines, which is very, very unlikely. But there is such a thing as a particle. In other words, the particle is a thing that is not continuous. That is the whole point of the quantum, is that it's separate. But if you think about separation, you're thinking about separation from what? From other particles. This is the theory of the photon, and it is basically the theory of the atom, which is based on the proton and electron. To make it simple, it's actually proton-neutron, which is a two-state object. But you can just say proton if you understand that in the background, protons and neutrons convert into each other. But those are actual particles. But I'm just going to call it one particle because it is just one particle. It's a proton that has two states, one of which has what we construe as an electrical charge, which affects the electron, and the neutron, which is the same thing as a proton without an electric charge. We're getting to that, but I just wanted to bracket what I'm talking about. This is actual physics. This is not theoretic. It's the interpretation that you need an interpretation in order to guide your research in the right direction so you actually finally get a solution. We haven't found a solution yet, and it's even difficult now, or it always has been, to state what the problem is. Well, Roger got it, and here's where you begin if you want to have a rational approach, which, of course, by definition, you do. So there are these two aspects of reality, one of which is a particle. Well, what's the other one? The other one is the wave. Now, Rutger knew about the work of Newton. Their lives overlapped. Newton had a corpuscular theory of light, which has since been substantiated. The particle separation that we're most interested in is the particle separation between the proton and whatever else there is. Well, we know whatever else there is. It only has one name, the electron. It is the electrons that give us the geometry of the Bohr atom. Now, I'm not going to go over that in great detail. That, of course, there's a corpus of knowledge about the construction of the atom. You can well imagine, even if you've never been exposed to it, it's certainly there, and right at the top of the list of what physics wants to know more about is the atom. Yes, of course. And there's been a lot of hype, because at the cutting edge there's going to be hype, and you and I are going to get drawn into it. If we're scientists with the right level of curiosity, we want to know what they know too, going down into the atom. So what do we know about the proton and the electron? What I'm going to do today is give you a slightly different, not really, it's not iconoclastic. It's not like this is a challenge to the theory. No, what science is looking for is a reinterpretation of the facts. We have a wealth of data about the proton and the neutron. The proton and the electron. But it's very difficult to put it into the correct model. And of course, science always wants to have a model if possible, but there's a danger in forming a model if you're not basing it on the right axiomatic principles. So I hope that that helps you understand why I have to rather ignore certain facts in order to get at pertinent facts. That's a form of concentration which has a balance. You have to be cautious doing that as well. For the same reason, you have to be cautious in making abstractions. You also have to be cautious in deriving some specific proposition from the more abstract facts. Now, the way Rüger formulated his basis for his approach to physics was essentially mechanistic, which is always to be preferred in a certain sense because you can test it. Now, he didn't have laboratory equipment, it wasn't anywhere on Earth, to analyze the atom. He didn't have any direct evidence of particles. So this is actually philosophy. And that's why he entitled it Theoria Philosophiae Naturalis. Now, natural philosophy in that day was the synonym for our word science. So it's not philosophy, which is kind of branched off into its own field, as we are well aware of now. But there is such a thing as scientific philosophy. Tim Maudlin and Bernardo Kastrup are they actually have degrees in the subject of the philosophy of science. So this philosophy is basically a synonym for the axiomatic basis. So what was his axiomatic basis that is now resurfacing in top echelon physics in certain restricted groups, because it's not approved of by the industry, and so it will be squashed. It'll be quashed. But it is known, it's already happened, and you can find this out on the internet. I should have links eventually, and at my page, anagalactic.space, which I'm going to resume work on soon, in conjunction with the publication of my document in Archive of my LaTeX document on my discoveries in geometry and mathematics. That's as close to a plug as you'll ever hear on this channel. Continuity is essentially the underlying word that we need for the wave phenomenon that Christian Huygens worked on. And his research is top-notch. You don't hear about it much, but if you're in physics, certainly in optics, you know all about Christian Huygens' work. And of course, one could expect that Bošković knew about Huygens' work. But he didn't talk about waves as such. He did talk about particles as such. Now, not even Newton did that, although Newton had a particle theory for light. What Bošković developed, and he is apparently the first man to have developed this, a robust mechanical theory of particle interaction. In order for him to develop this without any way to test directly what he developed, rather a heroic effort, I would have to say, but he was absolutely convinced of the validity of his work, and it's never been denied that his work was valid. Faraday referred to it, Bohr referred to it, a lot of people referred to it. Tesla is thought, although this has never been conclusively proved, I don't think, although I think it actually has been conclusively proved, a famous photograph of Nikola Tesla, who is Serbian, which is right next door to Croatia, which is where Bošković is from. They weren't contemporaries, Tesla came later. But Tesla is shown in this photograph with a book in his lap that is Theoria Philosophiae Naturalis. Now, Tesla didn't talk, I don't know if he talked at all about Bošković's work. I believe he did, but not extensively. But he knew of it. Now, Bošković, when he was first formulating his theory, which eventually dominated his work, and in the latter decades of his life, he devoted his work exclusively to his theory, which is based on continuity. Continuity is a philosophical point of view, but it's a scientific philosophy. Essentially, it's referring to wave mechanics. We do know of continuity. It's hard to give an example of continuity because it inevitably conflates a conception of particle individuality. And actually, you can't talk about either one without talking about them both. And in logic, formal logic, that's called a dichotomy. That's actually a word that I've developed to have this meaning specifically. It's a binary relationship, but it's dual. And the difference between binary and dual is that binary is on-off. When one state is true, the other one is false. But in duality, they're conjoined. And the perfect example of that is EM, electromagnetism. That's electricity and magnetism. But what those are a direct relationship between the phenomenon of electrical force. What we call electricity is conceived as a pressure in one formulation, whereas the associated phenomenon of magnetism is perpendicular to the electric field, and the magnetic field are considered to be orthogonal, perpendicular. That's an example of duality. That's not the same thing as binary. Because if they were binary, when the electrical force were active, the magnetic force would be nothing, it'd be zero. And they would alternate between electricity and magnetism. But they don't alternate. They occur together in a relationship. And that brings us to the nature of the two axiomatic terms that Bošković based all of his work on: continuity and impenetrability. The impenetrability, we're going to change that word to what we know that is. That's a particle. It's a thing. It's a quantum. And there's only one of those. There can only be one of those. It's not necessary that there has to be just one of those. There could be more than one kind. But it turns out from the research in physics in the 20th century, there's actually only one particle. Now that, of course, is not part of the standard model. They're dealing with particle physics at the model level. Everything is a particle. And you know there's about 36 of them now. You could say that, and in their system, their axiomatic basis is not Ruđer Bošković's. When you go right back down the funnel to where they begin, they're stuck with the word particle. Now, you and I are not. We're free to reinterpret the facts, and I have done so. So this does raise a huge question about the electron. Can that be considered to be a particle? That's what I'm going to talk about today. So, the actual indivisible particle of which Ruđer spoke is the proton. And that would have to be considered to be at least a unique particle. I'm saying it's not only a unique particle, it's the only particle. But in order to say that, I would have to say how the electron differs from being a particle. Can I say that? That's what I'm going to say, so that you can understand it. That's my goal in this presentation. So, when we look at the atom, it's very easy to see that it has a center. So already we have a difference in the behavior of the electron and the proton. Very simple, very easily stated. The electron is never at the center of anything. It's never a center. It doesn't make a center. It does the opposite of that. It makes a waveform around the proton. And we know that now. It's one of the major conundrums in particle physics that the electron cannot be isolated in its shell, that it's never at any one place. That's the definition of a wave. It's the definition of a waveform. And therefore the electron can be said to have two different states. When the electron is not part of an atomic system, it does appear to be a particle. So that needs to be confronted harshly. I mean, harshly against me. I have to be very, very careful to not leave anything out here. So I'm just going to go through this, but if there's something that you may have a question about, I wish this were a lecture hall. I should be lecturing at Madison Square Gardens or in some huge forum where there's a feedback. I could get questions from the audience, because that is science. It's how you learn. You have to ask questions. It's not an option. You must ask questions. But a good presenter, and this is not easy to do, he makes his presentation complete. But in order for it to get to the completion, there is a process. So you do have to exercise a certain tentative trust. Will I get to those questions that accrue along the way? Yes, I will. I swear to that. So at least hypothetically, accept the fact there's only one particle. And the reason I say there's only one is that a particle has to make a center. Well, the proton does that. So this is a relationship between the electron system and the protonic core. To keep things simple, we're just going to talk about one proton. But you know there can be up to 100 and even more, 120 I think, can fit before it starts to fission by itself. So it's from, we'll just say 1 to 100 protons. That at least covers uranium, neptunium, plutonium, there's a few more. But they become unstable after uranium. Just give it a cut off there. But if you have just one proton, that will have only one electron. There will never be two electrons going around one proton. I believe that's correct. No, that is correct, because helium, which is two protons, will have two electrons. Now, the number of protons can be, you would have to include neutrons, which can appear. Even in hydrogen has three, they're called isotopes. It has to do with the number of neutrons. So we're just going to disregard that. I know there's another huge footnote, but we're trying to get the axiomatic basis. So to do so, we make it as simple as possible. One proton, one electron. It is a fact which has been established in physics that the relationship between that proton and that electron is fixed. That is important, but it's only important in order to lead into a much more important statement, that the proton is always at the center, and the electron always makes a spherical shell. I just had a conversation with a fellow at a coffee shop lately. This doesn't happen too often, but when it does, I'm very grateful for it, because I love talking about this. And the man was fairly well informed enough to hear what I said, that I just said to you. And what he said, which could be expected, he said it's not a sphere, it's a spheroidal shape. That's true. Why would we have to stop and make that distinction, which he thought was important? I do too, but I was rather impressed that he brought me up on that, because I said it makes a spherical shell. Well, you could say that's correct, but you have to be a little more specific if you think it's important to be more specific. Well, in this case, yes. What it makes is a fuzz. The way we're able to measure the electron shells, which are geometrically spherical, the electron is never in any one place. It's very well known. It's very highly promoted as a spooky fact, because that gets people excited. Oh my God, that's something I cannot understand. Maybe the physicists will tell me more about it. Yeah, they'll try, but they're not going to do very well, because it is a waveform. If you say that, you're done. If you know what you're saying, that the electron is not a particle, not when it's in an atom. The electron is not in particle form. It's in wave form. and that's continuous. That's why it's so hard to measure. That actually, if you would, that is the quantum paradox. It comes down to the fact that you're forced to measure particles, particle position. You know, the Heisenberg uncertainty principle begins axiomatically with what you're trying to measure is a particle position. It has to be a particle to have a position, and in order to have a position, it has to be a particle. This is a identity. If you're talking about the momentum of something, it's the momentum of a particle, not the momentum of a wave. And the position, you can't get both. That's the Heisenberg uncertainty principle. Down to the Planck limit, you can get either momentum or position, but not both. You know why? Because the thing that you're trying to get the position of, at the same time you're getting the momentum of it, you can't, because it's not a particle. What is it then? It's a wave. And a wave does not have a position or a momentum, not in the conventional sense. All right, so now we know what we're talking about. When we say the proton-electron atom, the simplest atom there is, has a center. That is why I say that that alone is a particle. So, and that is the quantum. The essential definition of a quantum is the essential definition of a particle. But if you're treating the electron as if it were a particle or the photon, you can't do it. It won't behave the way you expect it to behave because you're expecting it to behave as a particle. Do we have evidence that the photon is a particle or the electron as a particle? You could say yes or you could say no. Physics says yes because it's biased toward the particle. Why? Because it has to be to make measurements. Because you cannot make a measurement in the same way on a wave because it has no specific position. So if you're treating the electron as if it were a particle, you might be barking up the wrong tree. I propose, with solid evidence behind my proposition, and this is not new, but it's not the favored interpretation, is that the electron is simply not a particle. That raises a huge question, because that thing can be fired from a gun, and it's conceived that, especially in the double slit experiment, which has been done both with electrons and photons, there's a behavior due to the construction of the double slit experiment that we do have what is believed to be direct evidence that the electron is a particle, and in fact that the photon is a particle. What I'm going to be showing you now is that is essentially the nature of the paradox, is to distinguish between two kinds of particles. And what I'm saying is there's only one particle that can be called a particle if you have a more specific definition of a particle that rules out the photon and electron. And then we have to turn to the photon and electron and deal with their particle-like nature. That is the quantum paradox. So the way I begin is by stating, with Ruger Josip Bošković, that the proton is a particle because it is a center of a system. The electron, it cannot be said of the electron that it is ever the center of a system. It's never a center. There's a reason for that that's elusive. It's been elusive to physics to state why the electron is never a center. All right. So we're going to deal with this in two phases. In the first phase, we're going to talk about the proton exclusively, although it's impossible to do so without talking about the relationship it has with the electron. That is the basis of atomic physics. The proton is unique geometrically because it makes a center. You can also say that it is a center. But if it is a center and it makes a center, that is a contradiction. Either it is the center or it makes a center. We can say that it makes a center based on the behavior of the electron, in this case just one, which is no longer a particle, if it ever was. The electron, when it's in relationship with the proton, is a standing wave. It's a spherical wave. It's a spherical waveform. We're just going to state that for now. But it's correct to say it that way if you complete the sentence this way, that the electron is a spherical standing waveform in relationship to the proton, and that is inassailably correct. What that means is the proton is the center of a spherical system. Here it's the simplest. There's not layers of shells as there are in more complex atoms. There's just one shell with one electron going around one proton. Well, then you have to ask, what is the proton? We can state what the proton is in several ways. And part of the work of the cyclotrons, or now called the hadron colliders, those are cyclotrons that collide particles together, as you know. Most of the research, I'll say the impetus for that kind of research was to get inside the proton, to find out more about the proton. Because what is that thing? We're saying that it is a particle, and the colliders, at least in that sense, prove that it is a particle because it can be fired and it can be accelerated and given an enormous amount of energy so that when it collides with another proton, it explodes. So, essentially. And things fly out, and then they measure what flies out. That's the nature of the CERN, the Hadron Colliders. So, and we don't want to get into that, but we might want to, so there's another footnote. But the proton is always the same thing. There aren't different kinds of protons. There's only the proton, and every proton in the universe is the same. That's based on a principle of homogeneity that is just assumed. Perhaps there's protons somewhere else. Well, then they wouldn't be protons, okay? They'd be something else, maybe a different kind of proton. All the protons we've ever found are the same. So we can assume that they are the same. We are locked on Earth. We can't be everywhere in the universe, but we're trying. So what that means is rather profound. This is a unique center of space. And I am saying space now. I'm introducing that term because there's a space around the proton. In quantum mechanics, this is called local space, as opposed to non-local space. And you'll hear those terms very often, particularly in what we wish could be an ongoing healthy debate between Bernardo Kastrup and Tim Maudlin, but they can't. They hate each other's guts. They can't be in the same room together. That was proved on the Kurt Jai-Mongol interview program. They will not even consider the other person's position. That's extremely unhealthy. Extremely unhealthy. And both Tim Maudlin and Bernardo Kastrup are off my list of people worth even listening to. So I'm trying to improve on the situation to get to the level that perhaps they might have been able to probe. What is this proton? What can we say about it that would help us in physics? I start geometrically. So did Ruger. So I'm going to give you our view of the particle. Now remember, I'm saying that the proton is the only particle. We'll get to the electron and photon presently, but you can definitely say that the proton is unique because it creates local space. And we know the geometry of the local space. It creates a sphere of influence. That's called a field. A very important concept, which is now attributed largely to Bošković. And you'll hear more of that, I hope, but you'll hear more of it from me. That's why Faraday referred to Bošković. Faraday was a hands-on experimentalist who was doing stuff that Ruger would have loved to be in Faraday's laboratory. Well, Faraday paid a compliment to Bošković by saying he's glad that Bošković had his physical philosophy, which included the concept of a field, because that is the basis of electrodynamics as well as many other theories, including gravity, which is also a field. Now, what is a field? It's a force that exerts spooky action at a distance. That's what it is. So it's no longer spooky if you say it that way, although it is still spooky. I always consider it spooky in seeing two magnets, if you orient them right at the correct distance, one will go right towards the other and crash into it. Well, that electron is trying to get to the proton. It can't. And the question is then forced on us, why does not the electron collide with the proton? We can state geometrically what happens instead. When the electron comes toward the proton, it reaches a certain radius and then spreads out spherically into a shell. That's a right angle in spherical space. It's a right angle in physical space. It's a right angle to the trajectory. It's being pulled in on a force line, and that's the correct use of the linear perceptual system that we have. We see straight line stuff. Well, this is a straight line that the electron is taking. If you look down the barrel of that, and there's the proton way over here, and the electron is going toward the proton, I'll do it the other way, going toward my nose. The electron is going, my nose is the proton, okay? And the electron goes straight toward it, and instead of hitting it, it spreads out around my head. Well, really around my nose. So I think you see that's a right angle. It's a spherical right angle. That's very interesting, isn't it? That the electron, which is considered to be a particle, and we'll say it is for now, but when it reaches that radius, it changes from being a particle to being a shell. And that is absolutely correct to say it that way. It is in one state, which is small. It's a little tiny thing that's heading towards another little tiny thing. But when it gets to a certain radius, it spreads out around the thing. And that's the electron shell around the proton. So those are two completely different things. In that relationship, they're utterly different. Utterly different. That is the solution to the quantum paradox. Not mathematically, not yet. But we can see it. That little tiny thing that's an electron that we consider to be a particle, I'm going to tell you what it is. It's an antiparticle. The electron is the opposite of a particle. And that leaves open the huge question of how come it behaves as a particle. In other words, it is a unit. That is the quantum of energy. What is the proton? It's the quantum of spatial contraction. It is the force center of a spherical force. It's a spherical force field. That's tautological. That's not guessing. That's not an interpretation. That is exactly what it is. It is a center of a spherical space field. That space is bent. It's bent spherically. How do we know that? Look at what the electron does. it goes into that shell. That's a force relationship. Bošković said that. He said that that's an attractive force that's drawing the electron, but when the electron gets to that radius, the force that's attracting the electron changes. So there's two forces at work. One is repulsive. That electron is no longer being attracted in the same way that it had been being attracted, because at the distance, an arbitrary distance, it's being pulled toward the proton. But when it reaches that radius, it is no longer being attracted. It's being repelled. That's a repulsive force. So let's talk about those two forces. Can we characterize those? Do we know of those two forces? Yes, we do. They have names. The force that's drawing the electron in, based on the protonic field, we can see the field effect of the proton. That beyond that radius, it exerts an attractive force. That's centripetal force. So beyond that radius is a centripetal field. A centripetal field. So anything, well, not anything, but an electron will be drawn straight toward the proton, and when it reaches, it's going through the field. It's a space field. It's going through the space field on a direct line, and when it reaches this radius, there is no longer an attractive force. There is a repulsive force. So it's being attracted, and then it reaches the repulsive limit, and it goes perpendicular all the way around and stays there. Absolutely stable. That has been computed how long that would remain stable. Longer than the life of the universe, according to the model. You could say virtually forever. It's a balanced system. One proton making a field which out to its radius is repulsive. That's the repulsive force of the proton. And beyond that radius, it's an attractive force. This can be plotted as a curve. That force field is attractive, and it starts out at maximum repulsion on one side of the radius. And on the other side of the radius, it's not repulsive anymore, it's attractive. That is a force curve. That's called the Bošković force curve. Newton did not know about this. And this is the improvement that Bošković made to the Newtonian mechanical system, which only knew about centripetal force. It did not know about centrifugal force. But the proton clearly manifests both forces. So the proton is not just an electron attractor. It's an electron attractor to a force balance ratio. And that is the electronic shell. Is that ratio manifest in space? That the electron will come in on a direct line, but when it reaches that surface of that spherical shell of the force, which inside is repulsive to the electron. In other words, the electron can't get in. The electron will not violate that limit. Instead, what it does is it changes shape. It can do so because it's not a particle. It's a wave. So now we turn to the electron. The electron manifests as a particle when it's not in an atom. So it does have, it's called the fermion radius, which has not been measured. It can't be measured because of Heisenberg's uncertainty principle. That thing that we call an electron does not have a position. And yet we know that it has a locality. So you'd have to say, and I'm going to say, that it's the inverse of the proton. Don't forget that that proton is not just bending space in. It bends space into a limit, a radial limit, where inside of that limit, it's still space. It's not the proton, but the proton has a repulsive force with respect to the electron. So it has a repulsive shell beyond which the force becomes attractive, an attractive force. That's called centripetal force. But inside that radius, it's centrifugal. It's centrifugal with respect to the electron. Now that's spatial. Remember that, because that's going to be important as we turn our attention now to the electron, which is also conceived to be a particle. Why? Because it has a locality. We know that it's there to within a certain limit, that it's probably there because it's less probably anywhere else. It's somewhere inside of a radial limit that we know that the electron is in there. So it's basically a calculus sort of thing. It's definitely there. We're not exactly sure where. That's the best we can say of the fermion electron. Well, we have a much more precise sense of the position of a proton. Why? Because it's a spatial particle. Because it exudes this shell around it, it has a center. Now, we can say the same thing of the electron, but not quite. And we're homing in on a paradox, and you're going to see it directly at some point. You might see the relationship directly at any time. And this is part of my goal, is to get you to see the relationship. But this relationship cannot be put into any known word system. That's the nature of a paradox, is we don't have any words to even describe what we're saying. But we have minds that are capable of doing the same thing in our own minds that we see in physical space. So the electron, we're going to say that it's an antiparticle. It's not the same as the standard model definition of an antiparticle, because the electron actually is known to have an antiparticle of its own, which is not a proton, it's a positron. And those two, when they interact, cancel each other in some way. This is highly esoteric. It's not fully understood how two particles can cancel each other. But it has been set up in experiments. There is an anti-electron called a positron, which was actually predicted by Paul Dirac, and then it was discovered, pretty much sealing Paul Dirac's place in history. But we're not really talking about, that's a charge relationship. And the charges apparently can cancel, and there apparently is such a thing as a positron. I don't deny or affirm that, but there is experimentation to show that these two different states of one particle exist, where one is the opposite of the other. The electron and the positron are that kind of opposite, and so the positron is the antiparticle. Now, I'm disregarding that because that's electrodynamics. This is not. This is the absolute nature of the electron, in which case you can say that there's a different kind of antiparticle relationship. I am saying that the electron has antithetical qualities with respect to the proton. Now, we're going to say that they're both particles in the sense that they have locality, but the locality of the proton is based on a field, whereas the electron, its quality is not that it exudes a field around it, making it a center of anything. It just doesn't do that. It doesn't create a presence in space. It is a presence in space. Now you could say that of the proton, but then you have to remember the proton manifests itself in space by a force field. The electron does not do that. It manifests its presence in another way. What is that? That is the fundamental paradox of the electron, is that it has a state presence. That thing can move, it can be fired from a gun, and yet it stays as a cohesive unit. But it's not a cohesive unit of space-force interaction. It's a cohesive unit of something completely different. We call that energy. We call that energy. Now, we know that the proton has two forces that it exerts beyond the radial limit of its more internal force field. Its internal force field with respect to this radial limit is centrifugal. This is in relation to the electron. That it has a centrifugal force that keeps it intact as a center. It makes itself its own center by a repulsive force, which is very short range. Beyond that, it's an attractive force to the electron. That's very interesting, isn't it, that it exerts two forces? All right. So the electron, we do know that it's a spherical manifestation. I won't go into the reasons for that, but you know that it has to have some kind of cohesion. Why doesn't it just disperse if it's energy? Doesn't energy just naturally disperse? Yes, it normally would. So why does this piece of energy hold itself together? It would have to be by some centripetal force. So the electron does have some kind of force that holds it together in spherical space. It does not fly apart. By the way, if it were to just disperse, then it's a photon. But electrons do not turn into photons. However, they produce photons. In other words, the electron, if it's in its shell state, okay, it has to be in its standing spherical waveform around a proton. If it's in that condition, for instance, our hydrogen atom, there's one shell of an electron. So it's a shell around the proton. At that limit between centrifugal force and centripetal force, it's balanced. That's actually a Lagrangian point in spherical space. Okay? That's why I talk about Lagrangian points a lot. That's where the James Webb Telescope is parked in a Lissajous orbit. So this is deeply synthetic. We're talking about pure physics now. The behavior of matter and energy. The spatial particle that forms matter is a proton, but the electron is an energy particle. It's not a space particle. It's an energy particle. Does that mean that the proton is not an energy particle? Well, it's a different manifestation of energy because force is based on energy of some kind. That's known. This gets a little spooky, but the force being exuded, making a field, the field force effect of the proton has to be based somehow in energy. We think of energy as something that accomplishes work. In this case, it's work in space. It's a force which can be said to come from some kind of energy, but in this case, we have to say that it's spatial, the spatial manifestation. if we want to call it energy to compare it with the electron, it's a space force. It bends space. That's a force. It has to be a force if it's bending space, because without the proton, the space is not bent. But in other words, electrons don't just go into a spherical orbit just anywhere. They only do it in the presence of a proton. So the proton and the space around it are in some way identified with each other. And that's why we can call it a force. But we don't want to exactly use the word energy, because energy is a different manifestation of reality. It's not the manifestation of space, a force in space. Instead, the electron is a manifestation of something else. We know what that is, but until today, I'll just say, until I look at it, I can see a different geometry. That the electron is not spatial. If you think of it as being in space, you're confusing yourself. Yes, you can say that it's in space, of course it is. But how is it manifesting itself? It's not manifesting itself spatially, not in the sense. In other words, the proton, in a sense, could be said to generate the perception of space because of what it does to space. But the presence of the electron, either as a shell or as a unit not associated into a shell, it's just an electron. We're just looking at the electron, whatever it is. It's a manifestation of something that is not spatial. Well, we know what that is. It's motion. The proton does not effect any motion. It influences the motion of the electron, but the proton itself does not exhibit an energic force. The electron does exhibit an energic force. It is actually a quantum of energy. That is a good definition of an electron. It's a quantum of energy. It's not a quantum of space. It's a quantum of energy. And that makes energy and space different. Does it not? So now we have to ask, since the proton manifests itself in space as a force field, the electron is manifesting itself in space, but not with a spatial force field. Then what is it? It's pure motion, but you have to say more. It's not linear motion. It's circular motion. It's actually spherical motion. It's, in some sense, the spin. That is motion. It's standing motion. That if you consider the electron to be a globe, like the Earth, it's spinning. So it means it's spinning on an axis. That is known. It does have an orientation in space. The Stern-Gerlach experiments prove that the electron is indeed a rotating sphere. The proton is not. The proton doesn't manifest any form of energy, unless you're willing to say that there are two forms of energy. And this will get down to the ultimate crux of the matter, is we're talking about the difference between spatial manifestation and a different manifestation that is not spatial. It's not spatial in the same sense that the proton affects space. Instead, the electron manifests its standing wave motion. That motion cannot be measured in space. Unless you think of the surface of the electron as constituting space, I suggest that now is the right time for you to try to split your mind or extend your mind to consider that that spherical thing, which is the electron, is not spatial. It's not space. It's something else that has at least 4 names. It's a manifestation of energy. It's a manifestation of angular momentum. It's a manifestation of periodicity. And it's a manifestation of time. So let's talk about time. That was the goal, and we're at an hour, so let's close this up. Time is real. Not only is it real, it needs to be defined much more carefully than it has been thus far in physics. Time is the manifestation of angular momentum. The proton does not show this at all. It's not based on angular momentum, although we'll get back to that. It kind of has to be. This has to do with its centrifugal force. Inside the radial limit of the proton is centrifugal force. Well, inside the radius of the electron is centripetal force. Something is binding it to its spherical shape. That something is hard to define, but I think you're starting to get a different, dualistic point of view of the relationship between time and space. It's better stated in another way. The proton manifests 2 forces, the only 2 forces in the universe, in spherical form, which we now know it is. Centrifugal, that holds the proton in one place so that it does have a shell, and beyond that, it's attractive force, that's centripetal force. The electron has its inner form conduced by a centripetal force that has not yet been identified what holds the electron together, but we know what happens when that's violated. In other words, if it's spinning, it has centrifugal force. The surface of the electron is centrifugal force, but it can't get out, and so it also manifests centripetal force. It's energy trying to get out, but it can't get out because it can't go beyond its own radius. And so whatever's holding it together is centripetal force, the same way that the proton is held together by centrifugal force. But beyond that limit, it's centripetal. For the electron, it's centrifugal force that's being held in by a centripetal force. And that is reciprocal relationship. We know that by the behavior of the electron around the proton. That when these 2 systems, one of which is centrifugal-centripetal, that's the proton, and the electron is centripetal-centrifugal, when they're related at right angle. It's not diametric. It's not polar. It's orthogonal. And that's Einstein's spacetime. I hope you enjoyed that. I hope that completes the previous lecture to a sufficient threshold that you're enticed to go on. There is much more. And it gets into mathematics, and this will be a satisfactory solution to the quantum paradox and much more. So stay tuned. This is Anagalactic giving you the secret of the universe, not plural anymore. This is the secret of the universe for physics that unlocks it. We'll be right back. Don't forget to keep